Hello everyone. In this lesson, we're going to be talking about another one of vector operations, which is called dot product or a scalar product. So let's look at what is dot product or a scalar product. So dot product is a reserved operator for vectors. So it's between two given vectors and is defined in the following way. So in the figure, you see vector A and vector B, A in red and vector B in blue, and there is an angle between them, and the angle is theta. So basically, to find the dot product between vector A and vector B, we need to place them at the same origin, as if we were to add them using the parallelogram technique. If you watch the video that I've posted on the channel on adding vectors, uh, one of the techniques is the parallelogram technique, and in that technique, we place the two vectors at the same origin. To take the dot product between two vectors, we will do the same. We will go ahead and place them at the same origin. And by definition, the angle theta is the angle between the two vectors. Now, I've written it up here. So the dot product, so we're not going to use in physics and in math, we're going to reserve this dot operator for the vector operator, and we're not going to use that for multiplication. And so here, as you can see, A dotted with B is defined as the magnitude of A times the magnitude of B times the cosine of the angle between A and B, cosine of theta in this case. So if you look at what I've done in the figure, from vector A, I've dropped a perpendicular line onto vector B. So this is as if we're casting a shadow from vector A onto vector B. So if there was a light source up here, let's say, shining light on vector A, it would cast a shadow on vector B, and the length of that shadow, by definition, would be A cosine theta. A cosine theta. We're going to be calling that A parallel. So A parallel, which is A cosine theta, is the component of A, is the component of A that's parallel to vector B. We also have another component which we're going to use in cross product or vector products, which is another video. We're going to do that in another video, which is going to be called A perpendicular, which is A sine theta. So this is not the one we're using in dot product. That's for cross product. So the one that we're using in dot product is the parallel component of A, which is A cosine theta. So basically, the definition of dot product is take the parallel component of A and multiply that by the magnitude of B. And the result is a scalar. The result is not a vector. That's why it's also known as the scalar product. So we're going to go through an example together. An example where the dot product shows up in physics is the definition of work. We actually define work in physics using dot product. So here's a question. In the figure that you see here, we have a box lying on the ground, sitting on the ground, and there is an applied force that's pulling on the box at an angle of 30 degrees with respect to the horizontal line, moving the box a distance of 5 meters. Calculate the work done by this applied force. So as you can see in the diagram here, we have the force drawn here at an angle of 30 degrees with respect to the horizontal, and the displacement vector here is d. So work in physics is defined as force, denoted here with capital F, dotted with, dot product with, d, which is the displacement vector. The displacement vector starts from the origin, from wherever the box was initially, and ends wherever the box ends up being. So the distance that the box moves in that interval is 5 meters according to the problem. And we're asked to calculate how much work is done by this applied force. So to calculate this, we just apply the definition of dot product. After all it said was take the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two vectors. So we're going to go ahead and do that. We're going to take the magnitude. By the way, if I write a vector without the vector sign, it does also mean the magnitude. So I can use the absolute value sign around the vector, that means magnitude, or I could just write like I did here, f without the vector sign, and that means the magnitude. So there is a difference between f with a vector sign, which means f as a vector, and f without the vector sign, which means f is the magnitude of f the vector. All right, so hopefully that clears it up. And same thing for d, so that's the magnitude of d, so 30 Newton times 5 meters, and cosine of 30 degrees, which is root 3 over 2, which comes out to be about 130 joules. All right, so this is the first time in physics that we actually apply dot product, in mechanics that we actually apply dot product. So very practical example of dot product. Next, we're going to do something a little bit more complicated maybe, but something that's essential and we do have to go over, which is taking a dot product when the vectors are in component form. So what we talked about with the definition of dot product was if they're given we're given the vectors uh, uh, and the angle between the vectors. So we have their magnitude and the angles between the vectors. But what about the case where what we're given is the component form? So here we have two vector equations, A equals to, and I'm doing this in 3 dimensions. So I hat, j hat, and k hat are the unit vectors, in 3D. I hat is in the positive x direction, j hat is in the positive y direction, and k hat is in the positive z direction. So a vector equation for A is given, ax I hat plus ay j hat plus az k hat. Vector B is also written as a vector equation, B equals to bxi hat plus byj hat plus bz k hat. What we're going through right now with this component form takes a little bit of work and focus, but the result is very simple and very easy to remember and very easy to apply. So for those who are interested to understand how this actually works, you got to pay attention to this. But once we derive the result, we don't have to redo this process every single time. We just end up just using that end result each and every time. But this is just done in a generic form right now. So what we do, we just first go ahead and write down the two vectors. So we're taking the dot product. We just replace the vectors with their vector equations. So that's the first step in the process. Next, we're going to go ahead and take the dot product between all the terms. So we have 3 terms in A and we have 3 terms in vector B, and we're taking that dot product, so that results in 9 terms. For example, AX I hat dotted with BXI hat, or AXI hat dotted with BYJ hat, or AXI hat dotted with BZK hat. That's just 3 of those terms. So those are the 3 terms that I have listed right here. All right. So just like that, we can write out all the terms. There are 9 terms there. I went ahead and wrote them down, and you can check them and write them with me. And the next step after that, after writing out all these 9 terms individually, is then the green. What I've written in green for you here is just trying to simplify that a little bit. So what we have is the dot product is a vector operation. So it acts on vectors. AX, BX focusing on the first term right now. Ax, bx, they are both scalars. They're both magnitudes. They don't participate in the vector product. So essentially we can end up writing the first term, for example, as ax bx, so we pull out the magnitudes, I hat dotted with I hat. So we start expressing each of these 9 terms just like that, pulling out the magnitude outside, and in parentheses writing out the unit vector operation, dot product operation that we have. So the second term is going to be ax by I hat dotted with j hat, etc. Then what we can do once we write down all these 9 terms is to go ahead and take a look at a pattern here. So if we have essentially these 2 cases. Case number 1 is right here, and case number 2 is right here. So case number 1 is when you have a vector like I hat dotted with I hat. By using the definition of dot product, so to do the component form, we still need to apply the definition of dot product. We have that to get I hat with I dotted with I hat, we have to do magnitude of I hat, which by definition is 1 because it's a unit vector, times magnitude of I hat, which is 1, again, a unit vector, times cosine of 0 degrees, which is also 1. So I hat dotted with I hat gives us a 1. J hat dotted with J hat with the same reasoning gives us another 1. These are all marked up in yellow. Then I went ahead and simplified the ones that had I hat dotted with I hat, J hat dotted with J hat, K hat dotted with K hat. So that whole main diagonal there ended up getting a 1. And when the 2 unit vectors are perpendicular to each other, like I hat dotted with J hat, you get cosine of 90 degrees, which is 0. So all those terms go to 0. So here 6 of those terms went to 0. And all that was left is ax bx plus ay by plus az bz. So essentially all we're saying is multiply the corresponding components, I hat components, j hat components, k hat components, and add them up. This is called the vector dot product in vector form or in vector equation. To apply it is really simple though. So here's a vector A in 3 dimension in component form. We can write it, not write I hat, J hat, K hat every time. Just write it like this. A hat in component form has components 2, 3, 0. That means it's 2 I hat plus 3 J hat plus 0 K hat in vector equation form. B has components -1, 5, -2. To take the dot product, as you see here, we multiply the corresponding numbers, components. So x components multiply, 2 times -1. Y components multiply, 3 times 5. Z components multiply, 0 times -2. And then we add them up. So in this case, we end up getting 13. I hope you enjoyed this lesson. Dot product is one of the most important ideas in vector operations, and I hope you can apply this to other problems and other ideas you're working on because it's a very crucial idea in physics. Thank you very much. See you next time.